Hello, Leiden Geometry students. In this assignment, we are going to talk about proportional objects. That's two different objects that are the same shape, but different sizes. In second semester geometry, we will do this with different shapes, like triangles, two triangles that are the same shape, but different sizes, or rectangles or pentagons. But for right now, we're going to talk about some real-life objects. And the first object we're going to talk about is this guy. His name, the tall guy in the middle there, is Manute Bol, or was Manute Bol, pardon me. Manute was, by all accounts, a very nice guy who led a pretty interesting life, but what he was famous for was being the tallest guy to ever play in the NBA. Manute was so tall he could touch the rim without jumping. He spent 10 years in the NBA. He was the tallest player ever at 7 feet 7 inches. Now, there's another guy who's tied with him right now, but I can't pronounce his name, so we're going to use Manute Bol. Manute's specialty, if you couldn't guess from his height, is defense. It was very easy for him to block people's shots. As you can see from this video, the quality's not great, but there's a block. There's a block. There's a block. There's a block. If you're a big fan of basketball, it might be worth checking him out on YouTube. It was very interesting to see people try to shoot while he was standing under the net. All right, we're also going to talk about another famous basketball player, or semi-famous. This guy's name is Muggsy Bogues. He was also a basketball player, and Muggsy was good. But he was not famous for being good. He was famous for being the shortest player in NBA history. Muggsy Bogues, the shortest NBA player of all time. Muggsy came in at 5'3" and spent 14 years in the NBA. He was actually a pretty good player, specializing also in defense, stealing the ball because people couldn't see him, and setting up his other players. I think he led the league in assists a couple times. But it was kind of comical sometimes to see him on the court. At one point, back in 1988, these two were on the same team at the same time. The tallest player ever and the shortest player ever. I know that picture looks like a dad taking his kid to the park or something, but those are two professional basketball players who were on the same team at the same time. Now, I'm going to change the facts here for just a second. Manute Bol was actually 91 inches tall, but we're going to say 90. It'll make the math work out really well. And Muggsy Bogues at 63 inches tall. That's 5'3" and 7'7" respectively. Now, back in the 80s, people not only collected like jerseys and stuff, but baseball cards and whatnot, and they also sold action figures of professional athletes. Here's the Manute Bol action figure, and the Manute's action figure was 10 inches tall. With this scale, how tall would Muggsy's action figure be? And that's the question we're going to try to answer. Now, you can do some estimating, but we can actually find out exactly how tall the action figure for Muggsy Bogues was supposed to be. And the way we want to do that is by setting up and organizing our information. What we'll use here is something called a proportion, and solving it is something you learned back in grade school, but we're going to apply it to a whole bunch of things. And the hardest part about these problems is the setup. And almost always the best way you can go about doing the setup is to realize that you have two different objects and two different measurements. In this case, our two different objects are people. Manute Bol, the tall guy, and Muggsy Bogues, the short guy. Those are their actual objects. And then we have two measurements, their real height and the height of their toy. So what we want to do is, even if you don't write all this kind of stuff out, is you want to organize your information this way. For example, Manute Bol's actual height, 90 inches. Muggsy Bogues' actual height, 63 inches. The height of Manute's toy, 10 inches. The height of Muggsy's toy, well, that's what we're looking for, so we're going to call it X. If we can get our information organized like this, then it's really easy to turn these numbers into a proportion. That's when you have two fractions that are equal to each other. Solving this should be pretty easy. All we have to do to solve a set of fractions like this, what we call a proportion, is cross multiply to solve. In other words, we're going to do 90 times x, that's going to be 90x. And 63 times 10 is 630. We divide both sides by 90, and we should get that Muggsy's action figure should be 7 inches tall. Now, we use this cross multiplying to solve all sorts of problems when we have two objects that are the same shape but different sizes. So what we want to be able to do is cross multiply. In case you need a quick review of cross multiplying, I'm going to do the problem here on the left and ask you to do the problem on the right. Basically, what always has to happen for us to be cross multiplying is we have to have two fractions set equal to each other, and one of the entries here has an x in it. Now, there's actually a bunch of other ways you could solve this, but cross multiplying makes it simple that even if x moves around a bit, you can use the same method for solving, and even if we make the problem a little bit more complicated, you can still use cross multiplying to solve it. So cross multiplying is this nice little shortcut we can use. So in the problem we just did, we did 90 times x, and that gave us 90x, multiplying diagonally. You're going to do the same thing in the problem over here on the right. you probably will need a calculator and maybe a little bit of scratch paper. Then the next thing we're going to do is we're going to multiply down the other diagonal. 63 times 10, we got 630, and you'll do the same thing in the problem on the right. Set them equal to each other, and we have a really simple Algebra 1 problem to solve. In this case, all I have to do is divide both sides by 90 to get 7. So the problem on the right, you should have done x times 21 to get 21x, 49 times 12, which gives us 588. Set them equal to each other, and divide both sides by 21, in which case we get 28 for them. Okay, here are a couple of really simple cross-multiplying problems. Use your calculator, use your scratch paper, or if you know of some other shortcuts. And again, there's more than one way to do these problems, but you're going to try to solve for x in each of these. Okay, in the first problem, we should end up with x is equal to 2. In the second problem, x is 16. And in the last problem, x should be 25. Now, you're probably rightfully thinking, hey, this is easy, I got this. Right, but there are some slightly more complicated problems that we'll run into in this class, and that's when we make it not just x in a problem, but a whole expression as either the numerator or denominator of one of the fractions, the top or the bottom. But the nice thing about cross-multiplying is we still take the same steps to cross-multiply and solve this. So let's say we have this problem. X plus 4 over 10 is equal to 1 over 2. We still cross-multiply. We're going to do 1 times 10. That's easy. That's 10. When we do x plus 4 times 2, it's going to look like this at first, x plus 4 times 2, and this should look familiar from Algebra 1. All you have to do is distribute the 2. 2 times x plus 4, well, we do 2 times x and 2 times 4, and that'll give us 2x plus 8. Now solving this problem should be pretty simple. We're going to subtract 8 from both sides and then divide by 2, and in this case, we're going to get 1 for our answer. And give you 2 other problems to try like this. Let's start with this one, numbered 6. Take a moment and see if you can solve for x in that first problem. Okay, when you do this, 3 times 20 gives us 60. X minus 1 times 4, we're going to have to distribute the 4. And we're going to get 4x minus 4 is equal to 60. Then we're simply going to add 4 and divide by 4 and end up with x is equal to 16. If you haven't done it yet, try the second problem. Okay, problem number 7 here, doing it the same way. We cross multiply. 6 times 21 is 126. 7 times x plus 2 is going to give us 7x plus 14. To solve this, we're simply going to subtract 14 from both sides and divide by 7, and we should get 16. Ooh, the same answer for both problems. Now, where do we use this? Well, we use this in all sorts of places, not just in specific geometry, but this is something that comes up in other places as well. And my favorite is where I remember my favorite childhood toy, which was Hot Wheels. I loved building tracks and racing cars down the tracks, and I particularly love this video because some guy found a way to put a camera on a Hot Wheels car and jump it over a track. And of course, my favorite thing to do was build the loop like most people. This is why I was so excited when I turned into an adult and found out that Hot Wheels sponsors an actual stunt driving team. And again, I know the quality of this video is not great. Feel free to check them out on YouTube. The Hot Wheels stunt team is pretty cool, where they build real-life giant racetracks and drive cars through them. They even paint the track orange so it looks like a little plastic toy Hot Wheels set. And the first question everybody asks is, do they do the loop? Yeah, they do. And here's an example. They actually made this loop. I don't know where they did this, but it's really cool. And they put 2 cars through that loop. So the math question having to do with proportional objects that comes with this. Let's say the toy car is about 2 inches long, and the toy loop, if you make one, it's about 10 inches tall. So if a real car is 16 feet long, that's kind of a long car, but 16 feet long, how tall would the real loop have to be? Well, just like with the basketball players, the best way we want to do this is organize this. We got 2 objects and 2 measurements for each one. We got the car and the loop in both, the real car, the toy car. And there's a handful of ways you could organize this, but here is a beginning chart. So what I'm going to ask you to do is take this chart, fill it in with the 4 numbers, one of them being an x, and that'll give you proportion, and then cross-multiply to solve for the missing height, the height of the real loop. Okay, if you do this right, the real car has a length of, the real car has a length of 16 feet. The toy car has a length of 2 inches. The real loop has a height of x inches. That's what we're trying to find out, or this will be in feet. And the toy loop has a height of 10 inches. And we're simply going to cross-multiply this to solve. So basically it becomes this equation. And if you haven't solved that, you should easily be able to do it. 2 times x is 2x. 16 times 10 is 160. We're just going to divide by 2 and get the height of that loop, which was 80 feet. We can apply this to all sorts of stuff. One of my favorite things to think about with proportions like this is one of them there Marvel movies where the little guy becomes a giant guy. So Ant-Man here, who's normally just 6 feet tall, grows into a giant dude who's 72 feet tall. So the question I'm asking here is how many times bigger did he get? So if we want to know how much larger he got, we just take the new height, 72 feet, and divide it by the original height, 6 feet. And you should get that he became 12 times taller than he was. That number, how many times bigger, or in other cases, how many times smaller he gets, that's called the scale factor. Scale factor makes for a nice shortcut when we talk about two objects that are the same shape but different sizes. See, if we knew the measurement, if we knew these two triangles here are the same shape, just different sizes, and if we know the measurement of one side, we can compare the two sides and figure out how many times bigger it got. To go from 2 inches to 6 inches, well, that's 3 times bigger. That times 3, that is the scale factor. And if we know that, we can find the other measurements. For example, this side down here is 5 inches. If I want to know the corresponding side in the larger triangle, I'm just going to multiply by that same scale factor. And in this case, the bottom of the triangle will be 15 inches. Okay, so one more proportion problem. And somebody who had way too much time on his hands built a scale model of Chicago out of Legos. You can see the Sears Tower there right in the middle. The Sears Tower is 1,450 feet tall. That red building next to it isn't really right next to it in reality, but it's close. That's called the CNA building. It's just an office building, and it's famous only because it's bright red. That building is 600 feet tall. If the Lego CNA building is 48 inches tall, how tall is the Lego Sears Tower going to be? So what you want to do is set up a proportion and cross multiply to solve. If you need help setting up the chart, your two objects are the Sears Tower and the CNA building. Your two measurements are the real heights and the Lego heights. Once you have that filled out, just cross multiply to solve. And in this case, you might have a slightly different setup than me, but you're going to have all these numbers, and the way you know if you have it right is the 600 should be diagonal from the X, and the 1450, the height of the Sears Tower, should be diagonal from the 48. When we cross multiply and solve this, 48 times 1,450, and ultimately divided by 600, we get that it's 116 inches tall.